Hello and welcome. So in this particular lecture, we will start talking about the algebra for SPARQL language. So the last few classes we talked about different constructs of the SPARQL language, and we have tried to see how we can write a very meaningful query and get answers from the real database, right? Now there we have made use of different constructs like optional graph pattern, union graph pattern along with the filters, and you can see this constructs, they can be combined together to come up with a very complex query, right? Now in order to write these complex queries, someone really needs to understand the real semantics of the individual constructs, specifically when the query involves multiple constructs together, right? Unless someone gets to know or understand the constructs in a deeper way, someone might end up with creating a wrong query, right? So that is one of the motivations for which we need to study SPARQL algebra. But the most important motivation to understand SPARQL algebra to write a SPARQL processor. So as you know that this is a language, right? So you are creating a query following a language. So you can think of this to be a parallel to a programming language where you know there are certain constructs of Python or Java or C, and using those constructs you can write your program, right? So you write one program one time and a completely different program other time, right? But your compiler does the job of processing the program and then come up with the meaning of the program so that it can compute different values based on the input, right? So you are doing exactly the same thing here. So you are writing a SPARQL query. So you are writing a SPARQL query. So this is your SPARQL query. Now it is following a language, right? Now, as it is following a language, there will be certain elements that you have written, right? Now, what you are doing really, you are putting this to a processor, which is basically will try to understand the query, and it will take as input a concrete data set, right? So this is where your RDF data set is coming, right? And for the processor first will understand the query, and in the second place will compute different values, right? And whatever you will be getting out of this computation will be your result, right? So that's the reason that first we need to talk about the grammar of SPARQL, and then we need to so after we have got this grammar and we have processed the or understood the query, then we have to represent the query into an algebraic form, right? We have to represent the query into one algebraic form, right? Then this algebraic form will be used to compute our result. So in this module, in this particular part of this module, which is part 4 of module 4, we'll be talking about the grammar of SPARQL, the algebraic form in which we can translate one query, and then given one algebraic form, how we can compute the result, right? So these are the kind of objectives we have for this unit, right? So if we try to talk about the summary of the SPARQL constructs that we have studied for the last few lectures. So basically you have got basic structures like you can define the prefixes, you can write where clauses, which is basically mandatory. Then inside the where clauses you can write different basic graph patterns. Then you can write like some group graph patterns, optional graph patterns, union graph patterns, right? And there are many other constructs. And along with that, you can define constraints through filters, and that makes use of the functions like bound, lang, regex, or different operators, right? And there are different output forms like select, construct, ask, describe, update, so on and so forth. And you know that there are different aggregation operations like max, min, average, count, sum. You can do variable assignment, all those stuff. And finally, we have got the modifier, so which modifies the solution you get out of all this. So you know these are the kind of structures will or constructs that will give you a set of results. Now, in many cases, you want to modify this. So the very basic modification is that you have got say 10,000 results and you want to limit that into say first 1,000 results, right? You might want to see the distinct set of results, not everything. You want to constrain your result by using something called having. You want to group your result. You might want to order your result. So these are called the modifiers, right? And we'll see that for each of them we have corresponding algebraic operator, right? Now, let us have a look at the bird's eye view of processing one particular query. And this particular example has been taken from the note written by Dave Beckett. So, this query is a very simple one. It is a very typical query having many things like select, from, where, group by, having, order by, limit. So, most of the constructs you can see that they are present here. Now, let us see how this query would be processed. So, first of all, it will look at the from data set. So, where from this particular data set will be or query will be answered, right? So, now you have got a data set as a graph that is coming into your next part. And in the next part, what you have, you might have mention of say graph patterns, sorry, graph patterns, right? Or you have observed that we can make use of service URI to query the databases remotely. Now, these are also some federated sources which you can take into account in your dataset. And finally, you have a where clause. In this where clause, you have different graph patterns. Basically, these are the kind of graph patterns which are present here. And using all of those, what you get a solution set, which is basically a list of records, which we will be calling as solution set going forward, right? Now, if you look at this set is not really a set because you have repetitions. You can have repetition for a particular record, right? So that's why this can be termed as a multi-set, right? So this can be a multi-set, right? So what you get essentially out of all this exercise, a multi-set. Then you apply group by operator, right? Now, after applying group by operator, you partition the data or the records in different forms, and for each partition, you can apply a set of aggregation functions, like you have got count aggregation function here, right? Now, at every step, you can see you are getting a multi-set as well, right? Now, after you get this aggregated view of the data, then you can apply some constraint using this having clause, right? Now again, if this as you are putting a constraint, some of the solutions will be passing the constraint or some others will be blocked by the constraint. Now the solutions that are passing the test provided by the constraint, they will be passed down to the next phase as a multi-set again or the solution set again, and then you can perform order by operation. After that, you can perform distinct operation, then you can perform limit operation, and finally, you can project your variable. So projecting means what are the kind of values you want to get as output, right? Now you can see that there is a clear workflow. So you start with something and end with something, and this workflow should be very precise. So the processor should know what should be the workflow given one query. So if that is not there with the processor, then you may end up with uh, mm, a result that is not really desired by you, right? So basically one objective of this particular unit would be to come up with a very clear workflow to process the query that we have in our hand, right? Now, talking about the processing flow, you have got different stages in this entire workflow. So first of all, the SPARQL query, the SPARQL processor will come up with an abstract syntax of the query. So what do you mean by abstract syntax of the query? So this is basically again similar to the processor that processes the programs following a programming language. So what do? They really create a syntactic tree out of the program, input program, right? So which block should be processed first, and then which blocks should be combined to come up with the new block, all those kind of stuff. And this is particularly called in the compiler domain to be the parse tree. So out of the program you get a parse tree, and that is basically following an abstract syntax, and this abstract syntax should be created out of consulting a grammar, right? So you can think of one sentence, and if you follow the sentence, in your sentence you have got, say, noun phrase, then followed by a verb phrase, and then followed by another noun phrase. This noun phrase can be starting with a determiner, then followed by a noun, right? A verb phrase can be having one auxiliary verb, then the main verb, so on and so forth. So you can see that this is becoming to be a tree kind of structure, and we will see that for SPARQL query will be having similar kind of structure, right? Now, after we get the syntactic tree, so we have got a very clear idea that what are the kind of relationship between different blocks in this query, right? Now, after we have got that idea in form of this abstract syntax, then we start to build the algebraic form of this query, right? And that will be done by assuming that you have got a set of algebraic operations which you want to use to represent the query in its corresponding algebra. And what is the motivation behind having this algebraic form? So that you can evaluate the expressions or the algebraic expressions that you have in this algebraic form of the SPARQL query. So you can evaluate different expressions. And if you evaluate this expression, finally we'll get a set of solutions, right? So this is a kind of very bird's eye view of the processing flow of a SPARQL query. Now, before going to the grammar, so first of all, as we understood that we have to have a grammar, and from this grammar you have to obtain one parse tree, and then that parse tree has to be represented in the form of algebraic form, right? So before proceeding to that description, let us talk about some basic definitions that we will be following subsequently. So let us first define what we mean by one RDF term. Now this RDF term can be one IRI, that is internationalized resource identifier. So this is basically, you can think this to be the URIs, but in URI you can use only ASCII characters, but in IRI you can use Unicode characters. So you can make use of any characters beyond the ASCII character, right? Now, the second thing that you have in RDF term is the set of RDF literals. So this is the IRI set of IRIs. So this is a set, and this is the set of literals, set of RDF literals, and this is the set of blank nodes. So this is the set of blank nodes, and together they give us the RDF term, right? Now we defined one RDF dataset to be a collection of different graphs, right? So you have a default graph. So here G is the default graph, as you can see here, Now each entry apart from this default graph is a named graph. So you have one name like U1 which is the URI1 and G1. So this is your graph 1. So this RDF dataset is a collection of unnamed graph as well as the named graph. So this is these are your named graph and this is your unnamed graph, right? I know that having a dataset consisting of various graphs doesn't ensure that all the graphs will be active, right? So that's why we need to define an active graph. So active graph is basically the data set, the graphs in the data set that are used to match the basic graph pattern that is there in the query, right? So everything else or the other graphs, they will be in a passive mode, right, or in a dormant mode. Now we need to define query variables, and these query variables, this is a kind of infinite set. So this V, which is the set of query variables, is an infinite set, right? Now this infinite set, and if you think of any variable in a query that is a member of this set, and of course this set is disjoint with the RDF term set. So you cannot really take any n member of the RDF term to represent that with as a variable, because we know that the variables, they start with always question mark, whereas the RDF terms, they do not start with this question mark, right? Now, how do you define one RDF triple pattern? So this is basically the subject. So subject can be one variable or one RDF term. The property can be one IRI or a variable. And you know that the property cannot be on blank note. So that's why we are using IRE here concretely. And then in the object position, you can have the RDF term and the set of variables, union of these two, right? So we can define a triple like this. So with this definition, so while we will be translating our query into its corresponding algebraic form, we need to decide on the algebraic operators or the vocabulary, right? So for every kind of constructs you have seen in SPARQL, you have one corresponding algebraic operator. So for example, for the basic graph pattern, we have got the operator to be BGP, right? So the BGP is the corresponding operator for the basic graph pattern construct, right? To represent group graph pattern, we make use of join. So this is the operator that corresponds to group graph pattern. So basically what it does, you have say two graph patterns. So this is one graph pattern and this is another graph. So basically you are joining them, and we'll talk about the definition of the join in the subsequent part of the talk. But this join is basically considering the joining of different groups of graph pattern, right? Now in optional graph pattern, you see again you are joining two graph patterns. So you have something like this. You are joining two graph pattern, but you are making sure that all the entries that you have here, they will be there in your result, but optionally you will be having the results from the right hand side. So this is your, so if you write it in a linearized form, so you'll be having a left hand side, then optional operator, then right hand side. So you have everything for the left hand side, but some optional thing from the right hand side. So this is also a kind of join, but as it is favoring the left part of the operation or the operator, we are naming it as left join. We again will be defining it very formally. Now union graph pattern is basically you are taking union of two graph patterns. So it is basically using the union operator to do that. And for graph pattern, we use the operator graph. For filter, we'll be using filter, right? Now after you have computed or imposed all the constraints that you have put in the form of the graph pattern on the filter, what you get a set of results. So this result is basically a solution sequence. So the results are represented as solutions, right? Now what you can do with these results, you can order them, right? So for that you use order by. You can select some a subset of the variables as your output. So you are having a complete set of the variables that are appearing in the query. So this is the complete set of bars in query, right? In queue, right? Now what you are taking as output, you are projecting a subset of this and selecting them to be in your outputs. So that's why this operator is called project, right? Uh, distinct is very straightforward. Sometimes you want to delete the duplicates. For that you will be using reduce. Reduced operator will not be used. There is another operator called slice, which will be basically representing the offset and the limit or the combination of, right? So these are the kind of operators that we are going to use to describe the algebraic form of a query, right? Now, coming to the language level processing of the SPARQL query, as we have mentioned earlier, that we have to have a grammar, right? So let us talk about the grammar, right? So what uh, you have basically the main component of our query is a where clause, right? So let us talk about the where clause. I guess if we have a very clear idea about that, then the other things will be straightforward to represent, right? So what we have in a where clause, in the where clause, we start with the keyword where, and that is followed by the group graph pattern, right? And you know, this group graph pattern is basically, it's a graph pattern combining complex things, right? So it is a kind of complex combination of all kinds of graph patterns you can think, right? So that's why your where clause is basically where followed by a group, right? Now we'll try to expand this particular idea. What is a group graph? So let us try to define what is a group graph. Now, a group graph pattern may start with a triple block. So, let us try to write down or take any example. So, you have one where, right? Then you start with, say, one SPO, right? S1, P1 and O1, right? So, you can have a block like this, right? Or you may not have a block like this. So, if you have a block like this, that will be happening at most once. So this question mark means that this triple block is either occurring 0 times, 0 or 1 time, right? So after you have a triple block like this, then this can be followed. So you can stop here, right? So you have just a set of triple, but it can also follow other things, right? Now these other things, they are something other than the triple. So that's why you are representing this as a graph pattern not triple, right? So it can be followed by something else. So that is a graph pattern that is not triple. Or it can be followed by a filter also, right? So finally, it can also contain another triple block, say S2, P2 or O2, right? And you can be having multiple. So you can be having multiple such statements inside the block, right? And this part you can see that this has been marked with a star. So that means this entire pattern that uh, mm, may appear 0. So it may occur 0 or more than 0 times or more repetition, right? Now let us try to expand this part, because this part is straightforward. Now when we try to expand this graph pattern not triples, so there we can have optional graph pattern. So we can have something like optional here, and then followed by another graph pattern, right? So we can have one optional graph pattern. We can have a group or union graph pattern. We will be expanding it again in the later part. Also, we can have one graph pattern. So one pattern can be followed by a graph pattern. So an example of that we have already seen earlier, right? Now let us try to expand this triple block. So what is a triple block? The triple block is basically a zero or more than zero occurrence of a triple, right? It can be having multiple triples or it can be having no triple, right? Now the optional graph pattern, it starts with one optional keyword and it is followed by a group graph pattern. Now you can see that this is a kind of recursive definition. So if we go back to the earlier slide, so you see that the group graph pattern can contain one graph pattern not triples, and this graph pattern not triples can contain one optional graph pattern. So that means one optional graph pattern may contain inside another optional graph pattern. So this is a kind of recursive definition of recursive representation we are talking about, right? Now, if we want to expand this graph pattern, basically it is having two representation. One is a graph keyword followed by one variable, then a group graph pattern, or a graph keyword followed by one IRI, then followed by a group graph pattern. Right? This is more or less straightforward. Now let us try to expand this group or union group pattern, graph pattern. So what we can have in this graph pattern? Let's say you have a group of triples here. So this is a group graph pattern, right? And then it can be having, it can join another graph pattern, which is again another group graph pattern. So you have one group GGP here, sorry, uh, group graph pattern here. Here you can also have a group graph pattern, right? Now you can omit this part altogether to have only one group graph pattern, or you can have a group graph pattern that is connected with this group graph pattern using one union keyword, right? So again, you can see that inside one union keyword or construct, you can be having another nested union construct. So because of the very fact that this is a recursive um, definition or recursive rule, right? Now finally, if we talk about the filter starts with one filter keyword and followed by a constraint, which is basically a boolean kind of expression. So let us take an example and try to illustrate what we are really talking about, or what we are really referring to the grammar of the particular SPARQL language, right? So as you can see here, you have this to be one triple block. Then it is connected to another triple block via optional. Then you have another triple block which is connected to another triple block using union, and then you are applying filter over the entire thing. So first you can see that you have got different triple blocks. So you have got different triples. You have got sets. Let us name it to be triple one. Triple one. This is your triple two. This is your triple three, and this is your triple four. Right? Now you have got triple one, and you are going to a triple block. I am doing a bottom up parsing. Right? You have got a triple block. So I'll write a triple block, right? Now you, so similarly you have got say triple two, and which is basically a triple block in our case. Then you have got triple three, you have got triple block, again another triple block, and 444, which is also triple block, right? Now you see that triple block 1 and triple block 2, they are connected via one optional. So they are talking about the optional graph pattern, right? So they are connected via optional graph pattern. Uh, so you have used something else, maybe, yeah, optional graph pattern. And these two triple blocks, they have been connected via union graph pattern, right? Now these two are connected via, so these are now joined by a group graph pattern. And finally, we are applying a filter on this, a filter pattern. So you see that we are creating a tree out of this query. So this is your abstract syntax. So basically you are creating an abstraction of this query so that multiple queries, though written in a different way, can be projected to a single abstract representation, right? Now you can see the similar representation we have created using this way, right? So this will be really the plan for your query. So how do you really process your query? Which part should be computed before which part? That will completely depend on this particular form of this abstract representation, right? Now, so we need to talk about how really we can translate one input query to its corresponding mm, so basically you want to translate a particular uh, mm, abstract representation of the query, abstract tree representation of the query into its corresponding algebraic form. And for that, you know that you need to have some algebraic operators. So these are the 5 algebraic operators that we are going to use. So the very basic operator is BGP. So what is P? P is a kind of pattern. So it can be a triple pattern. It can be something else. So this is P is really a set of results that you get out of evaluating a pattern, right? So you are really getting a solution. This solution is really input to your BPP. Now join, it takes into account two solutions. One is M1 and M2. We'll be representing the solution using the uh, alphabet M, right? Now this join is a conjunctive join of these two solutions. Again, we'll be having a more concrete discussion on what we mean by conjunctive join, right? Now join, we know that it is parallel to group graph pattern. So this is what is important to us at this point in time, right? Now this left join is a kind of optional join between two solution sets, right? Now you can see that there is something called F here. So F is basically a filter, right? Now it might so happen that one of these uh, entries, specifically M2 part of it, it can contain a filter or constraint which you want to need to satisfy. So in that case, F will be a parameter of this left hand, but this there you may not see any constraint imposed in the right part of the join. So in that case, this F will always be true. So everything that you get out of this joining, they will be passed uh, to the output stream, right? Now you have filter. So basically you have a solution set and you have a filter condition. If you apply this filter condition of the solution set, you get a filtered result, right? And finally you have got an empty pattern, which is basically it acts as an identity of the join. So if you join say M1 with Z, what you will be getting? You will be getting M1 itself, right? So it is acting as an identity of the join operator, right? So with this, let us try to talk about what would be our transformation algorithm. So we need to have one algorithm which we call as the transformation algorithm. What will it do? It will take as input one abstract syntax tree form, right? And then it will convert it into the algebraic form, right? Algebra expression, right? Now, before going to the description of the algorithm, let us take different cases and try to motivate our the development of the algorithm. So the case one is very simple, which is basically a triple block, and you know that we can represent that as BGP, and inside the BGP will be having a list of triple. So BGP triple pattern 1, BGP triple pattern 2, so and so. So this is our case 1, right? Now our case 2 is group or union graph pattern. So what is the form of this? So the form of this is G1 then union G2, right? Now this part, as we have mentioned in the grammar rule, that there is a star sitting over here. So this may be there or may not be there, right? So what would be the transformation in this case? The transformation would be the union of the transform of this and the union of transform of this. So why we are using the transform of this? Because this G1 can also be a group graph pattern, right? And that can also be a complex one, right? So that's why we need to first transform this and then take the union of these two, right? Now, if this part is not existing because of this star, then you just have this transform of G1 to be the uh, uh, value of or evaluation result of this group or union graph pattern. But on the other hand, you can be having two graphs, their union together. Then you can define the algebraic operation corresponding to this particular pattern to be union function, and inside the union function you have two arguments. One is the transformation of G1 and the transformation of G2, right? Now, coming to the third category case, which is the graph method, right? So again, what is the visual form of it? So it is having two cases. One is you are explicitly mentioning the IRA following by the graph keyword and then followed by a group graph pattern, which is G1, right? So what we will be doing? So you will be starting with a graph. So this is a graph operator which has got one IRI and then followed by the transform of G, right? So let us see. So this is the graph function. You have one IRI at the first argument and the second argument is the transform of G1. But also you can have in the second parameter to be one variable, right? So in that case, the corresponding algebraic representation of the graph, then the parameters would be the variable followed by the transform of G, right? Now you can have global filters. So why I am talking about global filters? Because the filters, they can be applied over the entire where clause scope, or the filter can be having scope only inside one say union graph pattern or one local say uh, optional graph pattern, right? So the form of a global filter is basically filter followed by a filter condition. So it is can be represented using this algebraic operator filter, and parameters will be having the filter condition, then followed by the transformation of the G on which we are applying the filter. So here we are assuming that we have already one G on which we are applying this. So this G is implicit here. So in case 5, you have optional without field. So what is the kind of visual we can think about? So you have one G1 connected to G2 via optional, and you can see that you just say left join because this is one optional operator, and you know that we will be representing optional operator with left join, and as parameters you will be having the transform of G1 and transform of G2, right? Now, the other case is you can be having optional with filter. So, optional with filter will be having this form. We'll see example later. So, you have one group graph pattern that is followed by one optional keyword, and that is followed by one group graph pattern, and inside there you have a filter condition, right? So, this filter condition is attached to the second graph, right? So, that is what we call as optional with filter. So, you have a filter with option. So in that case, you have to do a left join between G1 and G2, and of course the transform of them, and then the result of this left join have to be passed through the filter condition, right? So this is kind of a different thing than this left join, but we can represent them using a single construct. So how we can do that? So this is how. So we have this left join, and say I just say tr g1 and say tr g2 followed by say f, and this f will be the kind of filter condition that you have put here for this case, but for this case you can put it always to be true, right? So everything that you get out of this applying this left join operator on this, they will be passed to the output stream without any constraint, and that we can achieve by equating this f to be true, which is always satisfying. But here where you have a concrete filter condition that may be satisfied or may not be satisfied depending on the data set on which you are running your query, right? So, and we have a case 7, which is basically everything else, right? So you have everything, you have covered everything, every kind of scenarios. Whatever will be left with, will be joining them with the existing graph, and the element that we are left with, we have to transform that and then do a join, right? Now with this description of the cases, let us try to formulate the algorithm, right? So we are describing the function transform, and this transform function takes us input one abstract syntax tree kind of structure, and let us take this variable to be named as form, right? Now, if we will be talking about different cases, right? So, basically, we know that the case 1 is very simple. If the form is a kind of triple block, then the result will be the BGP of individual triple pattern. So, this is very simple, and this is your case 1. Now, coming to the case 2, which is your group or union graph pattern. So, what you have to, if we try to recall, you have G1, then union G2, right? Now you want to take the union, so you need to define this union between transform of G1 and transform of G2, right? Now we start with one uh, operator or parameter that is already undefined, so we don't assign anything to it, right? Now if you see that we have a graph which is group or union graph pattern, then we first check whether A is undefined. So we are considering this case, right? If A is undefined, then we transform this, right? We transform this. We transform the graph G1. So basically, we do transform over G1, right? Now then we'll be coming to the next part. Again, we'll be checking the element here. You have got this part. So I'll just try to refresh it in a clear way. So um, you have G1, then union G2, right? Now your G will be pointed to this first, right? Because we know that the pattern would be like this, right? So this is a kind of group or union graph pattern. Then A is undefined in the first place. Then what we do, we assign the transform of G1 to A, right? Then we come to this part, right? This is also a kind of a group or union graph pattern. Now here we have got G2, right? And in this case, A is not undefined. A has already been assigned some thing, right? Then what we do, we take a union between A, which we have already computed basically, which is transform of G1, right? And then we transform G2. So here we are doing the transform of G2, and we are defining it to be the union of transform of G1 and transform of G2, right? So this is the second case of our algorithm, right? Now this is the graph pattern. It is very straightforward. So if the form is a graph pattern, then we check whether this is of this kind of syntax where we have got the explicit mention of the IRI, and we represent that as graph IRI followed by the transform of the group graph pattern, which is following the IRI, right? So this is the kind of thing you are transforming, right? And we'll be doing similar thing for the variable, only exception that we are replacing this concrete IRI with the variable name that we have. So one thing that you should remember, that we are just converting the abstract syntax tree into the corresponding algebraic expression. We are not evaluating it, right? We'll be evaluating it later, right? So this is the third case of graph pattern, right? Now we are remaining with the, I think, the rest of the thing, right? So what we have, so we need to think about the filters. Now the query can have multiple filters, so that we have that, for that we have defined a set of filters. So it's a set. This fs is a filter set, and we start with an empty filter set, and G is an empty pattern we have started with, and Z is one empty BGP, right? So which is an identity for join, right? Now we just check that we take out every element of the group graph pattern. So this is the case for group graph pattern, right? We take out every element from the group graph pattern. First we check whether E is the form of filter or not. So if this is a filter, of course there will be a filter condition which is small f, right? So if this is so, we'll be adding this filter condition in the set of fs, right? Now if E is the form of optional, we haven't considered optional, right? And whenever we have got optional, in the optional we'll be having another pattern, right? Another expression, right? And what we'll be doing, we'll be trying to transform P first, and we see, if we see that this is a kind of filter expression. So this is the second argument of the optional. This is the second argument of optional, right? So so we are considering the fact that we have already seen the first part of the argument of the optional. So we have seen already the first part, and we are with this optional, right? And this optional is having a second part, right? And for this we have a P, right? So first we transform this P, then if we see, this is the form of a filter and A2, and what we are really talking about, so this P can be equivalent to a form like we have a triple block or a graph here. I not say triple block. We have a graph here in the form of say A2 and followed by a filter, right? So in that case, this is a filter kind of left join, right? So that will be converted to a left join operator which is having this as a graph. So G, we take out this A2. So this is your A2. So this is your M1, M2, and this is the filter condition, which is basically this one, right? If this is not so, if the transform of P is not of this form, so that means you do not have a filter here. You do not have a filter here. So in that case, you just transform this P, which is basically your A2, and you have already the transform of this. and you say that everything that you see you will be passing. So the result you get, you will be passing to the output stream. So that's why you are keeping the filter condition to be always true, right? So this is our case 5 of the uh, mm, cases, which is basically optional. So this is optional without filter, and this particular case is optional with filter, right, which is case C. Now coming to the case 7, which is basically everything. So this is the continuation of the uh, this part of the statement. This for loop is really continuing. And now if E is any of the other form, so this is the 7th case, any other form, then you transform E, and whatever expression that you have got, whatever graph you have got until now, you just take a join with that and the transform of this E. So we will be defining that using a join operator, right? So this is the 7th case, and finally we are left with the filters, right? So we have accumulated the filter while we are processing the things that are inside this while block, right? And these filters, so this set of filters are not the filters that are included in the optional, inside the optional block. So that is what you need to consider, right? So these filters, so these are not part of the filters in the second argument of the optional block, right? So these filters are the global filters. So you take a conjunction of all these filters, so and this conjunction will give you another Boolean expression, which is capital X, and you apply the filter of operator X over the graph that you have obtained finally, right? So this is going to be your algorithm, right? So this is the case 4, which is the global filter, and this is case 7. Now, I think in the next lecture, we'll be taking some example cases. We'll be playing with different queries with different kind of complex structures and try to see what could be their corresponding algebraic expression, and we'll try to see with ARQ-Jena whether we are really getting those structures out of the query, input query. Thank you very much.